Hey everyone, and welcome back for another deep dive. This time we're diving into some seriously cool research on machine learning and physics. Someone sent us a really fascinating stack of papers on this. Looks like someone's ready to explore the cutting edge.
It seems someone's interested in how we can teach computers to think a little more, like physicists do,
Yeah,
and maybe learn a thing or two ourselves along the way.
exactly. We're talking physics-informed neural networks, Hamiltonian mechanics, some seriously next-level stuff. But don't worry, we're here to break it down, ready to jump in.
Absolutely. Let's dive in.
Okay, so first up, physics-informed neural networks, or PINs for short. Now imagine you're a computer trying to learn, I don't know how to predict the weather.
Traditionally, with machine learning, we'd bombard the computer with mountains of data, temperatures, wind speeds, humidity, all that, and hope it figures out the patterns.
Right, like trying to learn a language just by looking at a dictionary. No grammar, no sentence structure. But what if we could give the computer a secret weapon? What if, alongside all that weather data, we also gave it an understanding of physics, thermodynamics, fluid dynamics, the fundamental rules governing how weather actually works?
And that's the beauty of PPNs. It's like whispering to the computer, hey, remember those fundamental laws of physics. Use them while you're learning. They bake these laws in as constraints guiding the learning process.
So instead of just throwing data at the wall and seeing what sticks PINs are learning with the foundation, they have a head start. Just like if you were trying to learn to ride a bike, but you also understood balance and gravity.
Precisely. That built-in understanding means BNs don't need to be spoon-fed mountains of data. They learn faster, they're more efficient, and here's the kicker. They're better at handling new situations that weren't in their initial training data. Because they know how the world works, they can extrapolate and adapt.
Okay. Are you ready to go deeper? Because we're about to dive into the world of Hamiltonian Neural Networks, or HNN.
Now, instead of just using general physics principles like PINs, HNNs take it up a notch. They focus on a very specific, very powerful concept, the Hamiltonian.
Okay, time to dust off the old physics textbooks. But for those of us who haven't exactly been brushing up on our Hamiltonian mechanics, what exactly a key as a Hamiltonian?
Think of the Hamiltonian as a system's energy fingerprint. It's a mathematical function that describes the total energy of a system, and crucially, how that energy dictates the system's evolution over time.
So HNNs are trying to learn this energy fingerprint. Why is that so useful?
Imagine a pendulum swinging back and forth. Its movement, its entire dance, is determined by the energy stored within the system. HNNs aim to decode that energy blueprint, allowing them to predict how a system will behave over time, with remarkable accuracy.
Now it's all starting to click, and you know me, I love when things get really tangible. You mentioned a paper in my reading list, 2004-09.11138v1.pdf. It talks about a breakthrough in training HNNs using something called symplectic integrators. What are those all about?
Ah, yes, symplectic integrators. They're kind of like the secret sauce that makes these HNNs so accurate. You see, with traditional methods, errors can creep in over time as you simulate a system's dynamics.
Right, like a clock that slowly drifts off time.
Exactly. But symplectic integrators are like atomic clocks for physics simulations. They're designed to conserve the energy of the system over time, which is crucial for accurate long-term predictions.
So thanks to these super accurate integrators, HNNs can now tackle even more complex systems, right? Like systems with tons of moving parts, all interacting in intricate ways.
Absolutely. We're talking about modeling things like molecular dynamics, predicting the behavior of complex fluids. The possibilities are vast.
From weather predictions to molecular dynamics, PANs and HNNs are already making waves. But, there's another layer to this whole machine learning puzzle that you've been digging into, right? It's not just about using physics. It's about how these models represent information itself, like what's going on under the hood.
Yeah, you're right. That's where things get really interesting. Instead of just memorizing every single data point they encounter, imagine a system that learns the fundamental building blocks of information, like discovering the atoms of data.
Okay, now you've got my attention. Tell me more about these information atoms. How do they work?
Okay, so think of it this way. Imagine trying to describe a picture, right? But you can only do it by listing every single pixel in its color. It's technically accurate, but incredibly inefficient. Like our brains don't work that way, do they?
Definitely not. I mean, we look for patterns, shapes, relationships, the bigger picture.
Exactly. And that's what this research paper, 249.1184v1WR, explores. It's about a new generation of models that learn a dictionary of essential information building blocks. So instead of memorizing the whole picture pixel by pixel, they learn to represent it as a combination of like basic shapes, edges, Textures, the important stuff.
So instead of a jumbled mess of data points, they're creating a more structured, efficient representation, kind of like organizing a giant box of Legos into separate colors and sizes.
Precisely. And this has huge AE implications for how well these models learn. Just like we learn better by understanding concepts, not just memorizing facts, these models become much more adept at handling new information, making accurate predictions, that sort of thing.
Okay, this is blowing my mind a little bit. We're talking about teaching computers to think more like us, but with the added benefit of being able to process vast amounts of data at lightning speed.
And here's the kicker.
Yeah.
The paper actually shows how these models can visualize those learned information atoms. So imagine actually seeing the building blocks of a picture as interpreted by a machine. It's like peeking into the mind of an AI.
Wow, now that's what I call a deep dive. We've gone from physics-inspired learning to the very essence of how information is represented. What an incredible journey this has been.
It really highlights how much potential there is in this field. By understanding how these models learn and represent the world, we might even gain new insights into our own cognition.
Exactly. It makes you wonder, what does it mean to truly understand something, whether you're a human or a machine? A huge thank you to you for guiding us through this fascinating and sometimes mind-bending landscape of research.
My pleasure. Always enjoy these deep dives.
And for you listeners, don't forget to check out the show notes for links to all the research we talked about today. We've also got a bonus question for you to ponder, inspired by that last paper we talked about, the 2-409.11376 v1.pdf paper on integrating these techniques with large language models. Could this be the key to unlocking even more human-like AI? Until next time, keep those brains engaged, and we'll see you in the next deep dive.